And today this will be our last lecture for this course, and I decided to talk a little bit about a very important notion in a theory of point processes, and this is so-called palm distribution. So at first, let me give some motivation in order to understand why do we need it and what is it. So assume that we have a point process so let it be in RD for simplicity of the form. So we have some number of points xi, so I just can enumerate them. And one of the important property of a point process is to understand the joint positions of those random points. And one of such characteristics is the smallest distance between some point, let's be x1, or from one specific point to other in this point processes. So I am interested in the smallest distance from a fixed point to all points in the our point process. So this question is not so simple because actually we do not. So the answer again depends on the position of this point. Yes, if the distribution of random points is not stationary, so the answer depends on the position. And moreover, we do not know exact position of the random point itself. So, but the approach in investigation of such a problem, so let me write the distance from a random point, let I fix x1 to other points. So I will write the point processes without this point x1. So this will be minimum distance. I write minimum of the distance. So I use norm xi x1 minus x yod, where yod does not equal to 1. So this is the definition of the distance. So I want to find the smallest, the closest point in the point process to x1. And we understand that this is a random value, so I want to understand the distribution of this random value. But one of the approach to find the distribution of such distance is to assume that we know the position of point x1. So assume that a point x is a point in this set xi. So In other words, we can say that we have mass in this point, and it is bigger than 0. So if we assume this, then this distance, so I assume that this point is number with index 1. So then I can ask the following question. So I want to find the distribution or the probability of the distance between a point x small and their other points in this point process. So let it be less than r small, with condition that x1 is equal x small. So now the question is to find the conditional distribution of some functionals of a point process. So here the question is how we can define the conditional distribution of a point process. So the question now is what is conditional distribution of eta. So with condition under condition that we have a point at x. I will write like this. So usually the probability of such event is 0. Yes, so usually the probability that some specific point belongs to a point process is 0. So we can define this probability in by the usual definition of conditional probability. So we need to understand how to specify this conditional distribution. Let's start from example. So if we consider binomial point process, so I recall that we have the some number of independent identically distributed points. So I consider them in 0, 1 squared, for example. So I have just on the square on the plane, I have some random points. And xi from 1 to, let's take m points, independent, uniformly distributed on 0, 1 squared. So I have such a simple point process. And again, I would like to find the conditional probability of the distance of some fixed point x to the subset x. I will write this random subset without point x. So I ask if it is less or equal than r, under condition that point x belongs to this subset of random points. X belongs to I from 1 to m. So on the picture, we can assume that, okay, I fix point x and I ask for the smallest distance to this point, and of course I can use the ball of radius r in order to specify this distribution. So I will consider the opposite probability, so I will write 1 minus the probability. Let me denote this distance like r small x. So this will be distance between x and other points in the point process. So I ask if Rx is bigger than R small under condition that X belongs to this subset. Let us start from the probability. So I can fix one of the point and I consider first that this probability that x is equal to x1, for example. So I consider such an event. And then I continue that probability that Rx less than R under conditions that x1 is equal to x small, and this is equal to 1 minus Rx bigger than R small. X1 is equal to x small. And what does it mean on the picture? This means that I have no other points. So if Rx is greater than R, that means that in the ball of radius R, I have no other points here. So this means that the point random points x2, x3, and so on xm do not belong to ball of radius x r. Okay, and since these points are independent, so by our constructions, they independent. So this is just unconditional probability. So I can write the probability that x2, x3, and so on xm does not belong to this ball. And now these points are independent also, so this probability will become true. Product of probabilities, so I just write here, and I have, let me write here, x IID uniformly on 0, 1 to the square. So I know that this probability that it does not belongs to some ball. So this is just the Lebesgue measure. I will write Lebesgue measure on square like this. So this Lebesgue measure of 0, 1 to the square without this ball to m minus 1. So it's not hard to calculate this. I think you can finish. So in such form, we understand that we can find the such a probability as a function of x small. And since here this event does not depend indeed in the index of x, so we can assume that we expect that this is the answer for the conditional probability. So this is the answer. I just will write it. This is our answer for the probability that we have are under condition that at point x we have a point, a random point. Let's consider another example with a stationary point process, because for stationary point process, actually we do not need to find the answer for every point x, but we can find the answer under the condition that we have a point in 0. So for stationary point process, we know that the distribution of a point process does not depend on shift. So a conditional distribution I will write by Rx, the singular distance. So this distance that we have x is greater than 0. Actually, we can find there that this is equal to if we have at 0 greater than 0. So this means that we want to find the closest or the smallest distance to other points if we assume that there is a point in the origin. So here will be there our R0. And for example, if we consider a stationary Poisson point process, we can try to find this conditional distribution by considering the sequence of smallest, the sequence of decreasing ball that decreases to origin. So what do I mean? Let us consider U, the ball at origin of radius epsilon. So this will be all x in Rd such that norm of x less than epsilon. And I will consider now R. I will write here epsilon. This will be the distance from 0 to a point process without this small ball. So I will write x I from 1 to infinity without u. So this is my small ball u, and I can have here some points of a point process, but I consider the distance only between 0 and points outside of u. And we suppose that when epsilon will tend to 0, this distance will tend exactly to the distance between 0 and other points in a point process. So let us try to find this conditional probability. So I will write epsilon less than r. Let me start maybe from this exactly. So, and under the condition that in ball U I have some points. So why do I need this notion of a ball? Because now I can use the usual conditional probability and write by the definition the conditional probability. So I have two events, and here I write the probability that I have a points in U. Now the next step is that let me draw a picture. That okay, let me write here. This value is bigger than r if and only if we have no points in ball of the radius r if I drop out U. So if this is equal to 0. Indeed, this is my ball U, and I say r epsilon less than or bigger than r. This is distance from 0 to some of the points, and I say that the points are all points are of the distance more than r. So inside in this here we do not have any point in the point. So with this I just write what is this probability means. So I just write it in all 0r without U. We have no point, but in U I have a point. And to make a next step, I will assume that we have a deal with a point, with a Poisson point process. So I continue my calculation for a Poisson point process. Assume that eta is a Poisson point process. What is the main feature of a Poisson point process? That their values of non-intersected subsets are independent. So we have that this subset and this, they are non-intersected, and here we use independency. When I write the independency, so I have a product of probabilities, and in the numerator and denominator, these values will cancel it. So in answer, I will write the answer. I have this is equal to 0. So now we can calculate this one. So since we have a Poisson point process, let me also write with that I have the intensity measure gamma times Lebesgue measure on R2. I will consider R2 on R2. Then I can calculate this value. So this is the expectation exponent minus gamma, and here the volume of this ball minus smallest one. This will be pi r square minus epsilon square. So now here we can tend epsilon to 0, and we will expect that the probability of that the distance from 0 to other points in the point process less than r, under the condition that at origin we have a point. I will write that we have exactly one point is equal to, so here I should write 1 minus e to the p r squared. So here you can see that this is a probability of that we have exactly we have no points in the ball of radius r in a Poisson point process. So here we understand the conditional distribution for such function. So this is the motivation for the next definition. So the definition of the conditional distribution of some of a point process with condition that a specific point x we have a point. And such distributions are called Palm probabilities or Palm distributions. So this is how we can try to define them. Palm probabilities. So we want to define the probabilities of some event A under the condition that at point X we have a point. So how to we will know such conditional probabilities, like probability of A with simple x here. So how we can define them in general case? And to do this, we have some technical but rather simple construction. We will do it using so-called Campbell measures. So let us define a measure on the space of a point process where it lives times space omega. So I recall that we have omega fp. This is our probability space. So let us define the following measure. Define a measure on a product for set B, so I have set of the Borel subsets of X, and A from sigma field A here. And I will define a measure C on this rectangular B times A. This will be just the expectation of the number of points in subset B, indicator of this random event. So I have a point process eta, and I define this measure. And then we extend measure C to all subsets of the sigma field that defined on the product of these two sigma fields. Okay, we can do this. So this is a Campbell measure. So note that if I take for the event A just or omega, I will have the intensity measure of a point process itself. So if I take A is equal to omega, I will have that T of B times A just equal to the intensity measure of a point process, and we write for intensity measure lambda, where I just recall lambda is the intensity measure of a point process eta. So with this in mind, we can say that for any A, we can write the inequality that this is less or equal than lambda of B. So if we have a point process with locally finite intensity measure, then I can, in such form, I can write a bound for Campbell measure. Now let us fix subset A and consider this Campbell measure as a function of subset B. So I will write this step, fix A, and let us consider we will denote it like MA of subset B. This will be just a Campbell measure on a product. So now I want to say that this measure now is bounded by intensity measure. So from this formula, I can write that this measure is bounded by intensity measure. And of course, this is a measure itself. So from this, now I will use the known result of the measure theory that I have. If I have such an inequality, then I can write that the measure mu I is absolutely continuous with measure lambda. So I will write. So I can use Radon-Nikodym theorem. So by Radon theorem, we can say that there exists a function. I will write it f. Of course, it depends on subset A because we just fix it. So I write that it depends on this subset A. The measurable non-negative function measurable such that mu A of subset B can be written as integral over subset B with respect to this function. And integral with respect to this measure, lambda dx. So this is now for free we get the existence of such a function. And since it's non-negative, and we can see that it is bounded by 1 from the definition. So we will consider this function f as just as a conditional distribution. So interpret that this is a probability of some subset and it depends on x. So here is we should say that we can find so under some condition we can find a regular probability. So I will write under some conditions. So they are satisfied for a simple case for us. So I will write that exists that f a of x is a measure with respect to A and measurable function with respect to x. Okay, so so we have something, some object, but we should understand that this is indeed what we are looking for. So let us understand this on the following example. So I will write it this because this is an important construction, but it was just for free by using the Radon-Nikodym theorem, and this is called Palm probability. So let us consider an example and take let eta be a Poisson point process. point process. And in the definition of the Campbell measure, let's take the following subset A. So we have event A. So let me take some compact set K, and I will say that event A is that we have no points in this subset K. So K is a compact set. So this is what I want to write. Now let us consider several cases, and first is I just take U disjoint with K. Disjoint with K. So this is some subset of RT. Then the Campbell measure by the definition C of U times A. So here we have U is a subset of RD and A is a random event. So by the definition, this is just the expectation of number of points in U, indicated that we have no points in K. So since I consider a Poisson point process, these subsets are disjoint, so I can use the independency on disjoint subsets. So I just write that this is expectation of number of points times probability that eta of K is equal to 0. So this is a intensity measure. So I just write lambda of U, intensity measure, times probability of event A. This is event A. Now, if I take the subset U that is a subset of compact set K. Then from this, we can see obviously that the number of points in U less or equal than number of points in subset K. So the Campbell measure in this case is equal to again eta of U indicate of eta of K is equal to 0. And since I have no points in K, so I have no points in U also. So this is just equal to 0. So now let us recall what do we have from the definition of this probability. So let me recall that we write this probability as let me write here, so we just denote this as C of B times A. Yes, we write it in a such form. So let us come back here, and I write in the first case, C of U times A. This is exactly the by the definition. This is the integral of subset U of probability x of A lambda dx. Yes, and so this is by the definition of px, the probability x, and in the first case we have this inequality, so that this is equal to lambda of u times probability of A. So in the second case, we have 0 at all, or C of u times A. So I just will continue that this is equal to x of A lambda dx, and this is equal to 0. So from this, I can write the equality for P of x of A, and it depends on where the point x is. So we know that this is all non-negative. So we have from the equality to 0, I can say that for almost all x of subset of u is 0. I will write here 0 if x. So here the case when u is a subset of k. So this means that x belongs to k. And here in the first case, u and u intersect k was equal to empty subset, so x does not belong to k. So, and in this case, we have just the probability of A. Probability of A in the case does not belong to K. So let us recall once more what is A. So I just write that A is the event that in subset K we do not have any points. So I can write now the probability with index x. Let me take the opposite. So I just write bigger than 0. And this will be 1 if x belongs to k, and just probability that it of k bigger than 0 if x does not belong to k. So here we can see that for such probability, we have 1 for if we know that a point x belongs to subset k. So if I have any subset k, so I will have here 1 if a point is here, and for outside of subset k, I have just usual unconditional probability for this process. So for the Poisson point process, for Poisson point process, we find that this probability with conditions that we have a point at position x is equal to just the probability if I add additional point x to a point process and calculate here k is greater than 0. So this is exactly what we get here. And this is a characteristic the characteristical property of a Poisson process. And in order to summarize what we did today, I will formulate the Campbell-Mack formula using the palm distribution. I will write it. So let us take a function f that depends on a point. So it depends on some points of a space X where, let eta be a point process on X with intensity measure lambda, and a function f is a measurable function from X times, I write here the space of measures. So let's take non-negative in order to guarantee that all integrals exist and be a measurable function. So this is a familiar for you expression. I will integrate the function f that depends on a point x and point process eta with respect to eta itself. And this is equal to the integral over space x. Here I will write the expectation with this symbol x. I will write and integral with respect to intensity measure. Where I will write where this expectation is expectation with respect to measure px, or we can write it as integral. This is a integral. So if I write here some measure mu, so this will be the integral with respect to this measure. And here's the space of all measures. So for the proof, I will not give you a precise proof here, but this is for the proof. You just need to start with specific for proof. Start with a function of their form as we have the indicator of subset B and indicator that subset that eta of some subset K is equal to 0, for example, and with such properties, so if you denoted this by A and consider, so this is the function, if you consider this function just expectation of x eta, this will be the expectation the integral, the integral with respect to process eta. So this will be the expectation. If you integrate, you will count the number of points in B. And with respect to second variable, this will be just the indicator of some subset A. So from this, you just write down by the definition of the probability of the palm distribution. This will be just the integral over B probability of probability x of A lambda dx. So this is just by the definition of this function. And next, what you should do, you just need to approximate all functions by step function of a such form. So I do not give precise steps, but I suppose that the idea is just from the definition of this probability. And for the end, I would like to compare what do we have already, because this formula, you can see that this is quite similar to what we already done on previous lectures. So let me copy it. And what we already did. So I want to compare this formula with known Campbell formula and Mach formula for a point for a Poisson point process. So this is Campbell Mach formula. So this is for all point processes, for all point processes with locally finite intensity measure. Then Campbell formula. So this is just simplest form of this one. I just recall that we can write it as following. So this was just the integral of f of x with respect to intensity. So here the case when x, when the function f does not depend on the second variable. So you can consider this formula as a simple case of the previous. F do not depend, does not depend on second argument eta. And the Mach equation was for only for a Poisson point process. So this was characterization of Poisson point process. So we say that eta is a Poisson point process if and only if we have that the expectation of integral eta dx is equal to integral, and here we write the expectation. So what we did, we add to the point process a point here, and then just integrate with respect to intensity measure. So here you can see that the Campbell-Mack equation that we get today is just the generalization of all previous formulas. Here we understood from the example that we considered that for a Poisson point process, the Pauli probability is that we just add additional point to a Poisson point process. So from this, we can say that for Poisson point process, we know that the expectation, the conditional expectation that we have a point in position x small, this is just as here we should write additional point for point process itself. So this is like a short summary of what we done, and the notion of Pauli distribution. We just give the brief definition and considered some example, but since we have this formula with using of the Pauli distribution, you can understand the importance of the conditional distribution of the Poisson of a point process if we know that we have a point at some point x small. So this will be the end of the lecture course of point processes. And thank you for your attention, and thank you for all who participated in the lectures. If you have some questions, you can ask.